Hi, this is Pyo, and in this presentation, I am trying to do the final project with project 2, number 4 on this slide here. Hi, so let's go over the problem here. So in this problem, we can notice that it's n equal to 1.5 and it's diatomic gas. That means that the CV equal to 5 over 2 R. And also Cp equal to 7 over 2R. That is the information given with the gas information. And then with the figure shown that the A to B is a isothermal process. And then B2c is there's no change with the pressure, so it's isobaric process. And then A to C is a isochoric, as the volume doesn't changes. So as the information given here, the question requests the work done and the changes in internal energy and the heat transferred from in the different kind of process, and also talking about the entropy here. In this slide, I'll talk about the focus on the A to B processes. As the question given, the A to B process is isothermal process, which means that the temperature doesn't change. So the change of the temperature is 0. Because the temperature doesn't change, so does the internal energy. There's no changes with the internal energy. That means because of the delta U equal to Q minus W. So Q minus Q and W is same, and because of it is an isothermal and process, we can have that the formula that is relate to the nRT log the final volume VB divided by the VA. And just plug in the number. N is 1.5 more, and then R is 8.314, and then which is a temperature we can get from the PV equal to nRT. T equals N PV divided by nR. And with the number given here, P is a 5 and V is a 10. But you have to notice that this is the ATM, so you gotta be careful with the unit. So it says 10/5, and then this one is a liter. Liter is a 10 minus 3. So divided by the NR, N equal to 1.5 and R equal to 8.314, and plug in all the thing, we get the temperature as around 406.2 Kelvin. And plug this number into here. So 1.5 times 8.34 and times 4062.2 Kelvin times the difference of the VB to VA, because it's given by the figure, we can notice that it's LM5. LM5 is around 1.6, so we can approximately calculate this is around 8, 800 153 joule, and because of the work done equal to the heat transfer, so this is the A to B process. A to B process, that is a 1553 joule was done, and then the heat transfer is also same as a 153. So let's continue with the A to B process here. In the A to P, we can notice that the entropy changes equal to the heat transferred with the temperature divided by temperature, because the temperature doesn't change it. And then we get the delta Q from previous slide, which is A153, and divided by the temperature is 406.2 Kelvin, that lead to the 20.07 joule per kilowatt per Kelvin. So that is our entire A to B process. So in the A to B, because it's isothermic, there is no changes with the heat. The lead to the internal energy doesn't changes. And then the work done is equal to the heat transferred. So that is we calculate by previously is A153 joule, and then delta S get previously is 20.07 joule per Kelvin. That's for the A to B process. In this slide, we will focus on B2c process. As we talking about in the beginning, B2c process is the isobaric process because of the P is 1 atm, and there's no change with the pressure, so that the work done is equal to P delta V. And also, because of no changes with the pressure, the heat transferred is zero. Because of the heat transferred is zero, so the internal energy equal to negative W, because of delta U equal to Q minus W. So we can easily get the W with the P delta V. The delta V is that the last point C minus B, so that is 10 to 4 or 50, so that is negative 40 times is 1 atm. And just transfer it to the SI unit, so we can easily get this is 4,000 joule, because of liter equal to 10 to negative 3, and 1 atm is 10 to fifths, and times it is 10 to 2, and 40 is 4,000, and then of course that's minus. And delta U is equal to negative W, so that is 4,000 joule changes in internal energy. Continue with the B2C process, because of it is a isobaric processes, we can get the delta S in entropy equal to NCP times log of the change of the temperature, which is the Tc to the Tb. So that is N is 1.5 mole, and Cp is 3.5 R, because of its diatomic. R equal to 8.314, and the temperature changes in here is literally is the change of the volume. So we can write as the Tc to the Tb equal to Bc to the Bb. It's also because of the ideal gas law, which is the nRT equal to Pv. Because the P doesn't change, so the change of temperature is equal to the change of the volume. So we can get the correlation relationship in here. So just plug in the number 1.5 mole times 3.5 times 8.34 and log volume C is 10 and volume B is 50, so it's log 5, negative log 5. So after calculation of this, we can get the number of the entropy here as a 70.2 joule per Kelvin. In this process, I am talking about C2A processes. In the C2A process, we can notice that C2A, the volume doesn't change. The volume doesn't change means that this is isochoric process. In isochoric process, we can notice that because of the volume doesn't change, the work done is zero. And because of the work done is zero, the internal energy changes equal to the heat transferred. And because it's isobaric process, we can using delta U equal to the change of the NCV and the temperature changes. And the temperature changes equal to the NR over PV. And because of the V doesn't changes and the energy change, the pressure changes, we can just make it the delta PV. And we can plug this number into here. In the CV, because of its diatomic, so we can get the 5/2R and then plug this function into it and then consolidate to get the delta U equal to 5/2 PV. And the volume doesn't change. The volume is 10 liter, and then delta P, the entire process, we can notice that the change of the energy is related to the delta P only. So that is 4 ATM changes. 4 times 2.5 is 10, and the V is 10 liter. But that is just write it down. That is much easier to. So 10 times 10 minus 3, that is 4,000 joule changes in the internal energy. And because of the 4,000 joule changes in the internal energy, the Q equal to 4,000 joule as well. Continuing with the C2A process, we can notice that the C2A process is isochoric process because the volume doesn't change. So that means there is a entropy changes equal to capacity of NCV time and times log of the difference of the temperature. So C2A, so it's TA to TC. So with the ideal gas law, we can get the nRT equal to PV, and because of the volume doesn't change, and those are constant, we can get the TA to the TC equal to PA to the PC. So just plug into the function which is here, and CV is because of that diatomic gas. So this is a 2.5 R. 2.5 times N is 1.5 and R is 8.314. And the temperature rate is same as the PA to PC, and then PA is 5 atm and PC is 1 atm. So this is literally log 5. And after calculation, we can get this number is 50 point. Just let me do it again. Just wait a second. So 2.5 times 1.5 times 8.314 times log 5 equal to 50.18 joule per Kelvin. In this slide, I will wrap up entire information together. So as we calculated in the A to B processes, there's no internal energy changes, and the W equal to the A153 joule. And Q is equal to W, so that means that the same as that. And delta S equal to Q, delta Q divided by T, and there's no change with temperature. We just divide this number to the temperature, we get as a 20.07 joule per Kelvin. And in the B2c processes, we get because of there's no change with the pressure, the Q equal to 0. And because of the Q equal to 0, the W and delta U is negatively procyclical, or we can say that W equal to negative delta U, and the W equal to P delta V, and the last volume is lower than the initial volume that lead to the work is done is negative 4,000 as previous calculation. That means that the internal energy changes 4,000 joule as well. And after calculation with the entropy, with the information of the diatomic, this kind of information, we get the entropy change in this process as a negative 70.2 joule per Kelvin. And then in the C2A processes, we notice that there is no change with the volume. That means the work done of this gas is 0. That means the delta U equal to Q, and after calculation, we get the 10 to 4 joule or 10,000 joule. And the entropy changes we get as a 50.1 joule per Kelvin. So as you can notice that this is a reversible cycle, so that means there's no entropy changes, and as a result we can notice that the change of the entropy is very minimal, or there's no changes in this process. And in the internal energy wise, they find that there's 14,000 joule internal energy transferred into the system. And then in the work wise, we know that the entire work done is 8153 joule minus 4,000, that is a 4153 joule. And the heat transferred is 118 153 because of the no, not because of, it's just after the calculation. And so efficacy of this system is that the sum of the work divided by sum of the heat transferred into the system. So after calculation, I get the 23% of the efficiency. In order to get the highest efficacy, we need to make a system as a cardinal system, right? So in the cardinal system, it has the efficacy, which is the lowest temperature over the highest, the lowest temperature over the highest temperature. In this system, TA and TP is highest, higher, and temperature, and TC is lower. So we write the highest efficacy as this function. So that lead to that the TCC to the TA, we know that is 1 to 5. That is simply to 80% after calculations. So 80% of the 1853 is the maximum heat we can transfer into system. That leads to the maximum heat we can transfer is 80% times 18153. We get the 14,522 joule. So I think that's all the information or the question we ask, and there's no entropy changes as it's a reversible system, and we can notice with the figure as well. And then there is tons of the internal energy, which is 14,000 joule internal energy going into the system in a cycle. So yeah, that's all for this problem. That's it for my number 4 question. And thank you for Professor to support us in presenting and then to prepare us to in these courses. And thanks a lot. Thank you.